when you wanted to characterize milling, or milled particles.
Particle shape, size.
No, the type of name of the distribution that we use to characterize.
Frequency distribution.
That's like common, right? The way we plot the right size or density, like frequency or cumulative distributions. Okay, but I told one name that's specifically used for we are like milling particles. Anyone remember? No, name like normal distribution, log normal, and I mentioned one more. Good memory than me, okay. But might go ahead.
Histogram one.
Now histogram is a regular, plot. Again, as we talked about yesterday, do not plot histograms, but plot frequency distributions. Okay, histograms might give you error, but for plotting frequency, then you can avoid some error. Okay. So it's a Rosen-Ramler distribution, right? Okay. You might Rosen-Ramler, or sometimes it's, if you change the constants, we call it as Weibull distribution. Okay. I didn't mention Weibull, but I mentioned Rosen-Ramler. But what is the any biological agricultural material? What is the distribution that they fall into commonly? What type of distribution they fall into? Normal, log normal, Weibull. So you have three options. Okay, normal. Okay, you have two more options. Okay. Any type of biological materials, okay, mostly if you take anything, they very rarely fit into normal distribution, log normal, right? So most of the time when you see the distributions, they fit into log normal distributions. Even for particle breakage, forces acting on grains, any type of size distributions of grains, powders, you most commonly you'll see log normal distribution. They fit very well in log normal distribution. Okay. Okay, so moving on. So what else did we learn? You said porosity, right? So what else? What we learned in porosity? You all are calm today.
Types of pores.
Types of pores, okay. What else?
Porosity.
Porosity, okay. So to get the pores volume, right? So what is a common method that we use to get porosity or pore space? X-ray microtomography, that's little expensive, but mercury is common, but it's reduced. They've almost around the world they've reduced the use of mercury, so you may not use mercury. Okay, and there are a couple of equations that we talked about, to find the pore space, right? Anyone remember? One for laminar and one for laminar plus turbulence. Anyone remember those two equations? Okay, Karman-Kosny and Ergun relationship, right? So Ergun relationship accounts for turbulent flow, right? So you asked about the constant, right? 180 and 1.8, but the constant for incompressible flow through the pore space, and assuming the pores are in straight line, so Ergun used that constant 150 and 1.75. Okay. So assume spherical particles and the pore spaces are straight. Okay, and then there will be laminar and turbulent flow inside, but we use those two constant values. Okay, so there are some those are constants. So many others have used different constants. Thank you. Yeah. Many others have used different constants depending on the Reynolds number. So if the Reynolds number changes, I know you guys don't study about Reynolds number and stuff, right? In agriculture, right? Do you study? No, those four people. They are from agricultural stream. So, but Reynolds number is to characterize fluid flow. We use for powder flow too. Okay. So based on the Reynolds number, those constants change the values. Okay. Okay, so today we'll talk about particle density. Okay. So this again, one of my picture from one of my students' work on getting pore space or white space using X-ray microtomography in fertilizer granules. So our work was to, change the porosity inside urea granules and, change their dissolution pattern, okay, how they dissolve. Okay. So when we talk about particle density, what comes to your mind? Why we should care about particle density? Okay, mass. Then what else? Mass. Oh, what is that? Don't go into then I will have to ask about what's the difference between weight and mass. What is the difference between weight and mass? Okay, 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 that's correct. But it doesn't play a role here. So we usually take mass. Okay, we usually use mass, but what we do in labs, we take the weight, right? We don't take the mass. So, but that's common. Okay, but talk about particle density. Again, we'll go through them. So how many different types of density you can think of? True density? Okay. Bulk density? Tap density? Very good, yeah. There's one more. Okay. But we'll talk about, but those are for bulk powders, okay? But this is, we'll talk about particle, okay? But particle density, but if the particle density, if the particles are of very small size, it will be very difficult to measure the particle density, okay? But we use different approach to get their particle level, density. One is again X-ray microtomography, okay? So the one that you guys didn't tell was compacted density or compressed density, compressed bulk density under pressure, okay? So but we will talk about that when we go into the next lecture, okay? So again, particle density is similar to bulk density or powder density. It affects flow, segregation, almost how much you ship, how much you handle, etc. Okay. And again, simple example you would have about bond number, and I briefly mentioned in one of the lecture too. That's the ratio of resistance flow, inertia, and then the viscous flow, okay, or the resistance and the inertial forces. Okay, so in general, if the particle density is increasing, the flow behavior will be little better. Okay, so why the flow behavior will be better? Again, the density is high, so the inertial forces will be high. Okay, so bond number goes down, and then the flowability will increase. Okay, it's again 10. Okay, and segregation. Again, this from experimental work. It definitely affects segregation, right? So we briefly talked about Brazilian nut effect, right? Segregation of particles based on size and density. Density also affects. Okay. So again, if the densities are of almost similar, you might not see very much segregation of particles within the bulk. But if they are like highly different, then you will see kind of segregation. So why it's important? During mixing process, if you're making some formulation, if you're going and working for a food industry, where you make some formulation for example infant formula. Okay, so infant formula, if you are making an infant formula, you will be mixing at least 5-6 different types of powders. Okay, but their densities will not be the same. Okay, so when you mix, then again there will be a high potential for segregation. Okay. So since we talked about infant formula, suddenly it came to my mind. In West Bengal there are lots of lotus, right? Lotus flower, right? Do you know what's the use of lotus seeds? Why do they use? When I was in CIFET, we developed one lotus decorticating machine. I'm not sure if it's still working, but lotus seeds are very hard, but it's very difficult to break. Do you know, there will be starch inside the lotus seeds. Anyone know what's the use? purpose?
We are using for eating makhana. That
No,
are same or different?
no, that's different. Makhana is different. Yeah.
But sir, makhana are also same aquatic seeds, same like that.
Maybe, yeah, I do not know much about makhana. Yeah.
So both are aquatic or similar kind of these things.
Oh, is it?
Yes.
Okay. I didn't know. Yeah. Okay. So lotus seeds powder is highly nutritious. Okay. So they add an infant formula. So it's lots of lotus seeds are exported from West Bengal to Singapore, US, Europe, etc. Okay. It's a big time export from. Okay. So again, yeah. So offline, but again, depending on the density, the powders segregate a lot. Okay. This is another example. If you are making compacts, okay. So I'm not sure how many of you seen compacting machines or tableting machines. It's common in food industry, common in pharmaceutical industry. So in a tableting machine or a compacting machine, usually there will be a shoe where you fill the powder, okay, and then the pressure is applied and they make it into compact. Okay, then it will be ejected. Okay. So if the density is different, what happens? The lighter particles will segregate, okay, and then your formula mix within that compact will not be uniform. Okay, so they may not have uniform dissolution property or uniform nutrient release properties, etc. Okay, again, that's another big problem. Depending on the die size or shoe size and their width and depth, density has a major role. Okay. So what they usually do is add some air, okay, add some air or pull the air out. So if there is air, then there will be higher turbulence, okay, and there will be higher segregation, okay, or you pull everything, all air out, so that the chances of turbulence is very low. Okay, again, usually if there is some air inside, it inhibits flow and there will be higher potential for segregation. Okay, so again, role of density. Okay, any questions so far? But we will talk about bulk density, powder density later in the next part of the lecture. Okay, so how do we measure particle density? Okay, which picnometry? Oh, you do not do, okay. Yeah, anything gas or liquid picnometry. Either you can use gas or you can use liquid too. Okay. What's that? Yeah, liquid also you can, depending on the solid. Okay, you can use, when you are using liquid picnometry, you'll have to use, non-absorbent liquids. That's only, condition. Okay. So true density, again, follow these pictures here. Okay, true density is the density without counting any void space or without including any pore space within the solids. Okay, just the pure solid, mass of the pure solid and volume of the pure solid. Okay, so if you get the mass of pure solid without any void space and get the volume of just the pure solid, okay, it's almost like here, and you can see in this picture too. So that's the true density. Okay, again, true density, you cannot calculate by liquid picnometry or gas picnometry too, right? Because the internal pores, you will not be able to access, both gases and liquids will not be able to access the internal void spaces. Okay, so only way you can get true density is by chemical analysis, or you have to grind it to maybe submicron level powder, and then you can get maybe a little bit higher, little accurate true density measurement. But in general, you may not be able to get the accurate volume unless you are using any chemical analysis, okay, by chemical. But most common density that we measure is the particle density or the apparent density, right? So that will, the volume, when we calculate the volume, that will include the internal void space or internal pore space too. Okay, so mass is almost same, but the internal pore space and internal void space will be counted or included in the volume calculation. Okay, so which density will be higher? The true density, right? So since the volume is low, always the true density will be higher than the apparent density. Okay. But another common density that we characterize is the aerodynamic density or the envelope density. Okay. Envelope density, you still include the external void space in the volume calculation too. Okay. So those external void spaces are included, okay, in the volume calculation. So this value will be still lower than the apparent density. Okay. So these are the three common densities that characterize for particle. Okay. True, and then particle, and then envelope density. Okay. So as I said, always true density value will be the highest one. Okay. And then the envelope density will be the lowest when we compare these three. Okay. Any questions? No?
What do you mean by external voids? How you are calculating the external voids?
So the external voids, we'll talk about in a minute. How do we do that?
Irregular shape, you were just making it regular and then you were counting?
You may not be making it regular, but just if you have example, you see this kind of solid, you have lots of pore space inside, so you are covering envelope, like putting a envelope around, like shrink wrapping it with a plastic, and then taking the volume of the solid. Okay. So it's not that we are making the circular sphere or anything, just wrapping it. So when you wrap, you can see all the internal void space, everything will be included in the volume calculation. Okay. Any questions? Okay. So again, particle density, as we talked about, it includes the volume calculation, include the internal, the granule. Talking about the granule porosity, right? Sorry. So the porosity, we can calculate from this density calculation, right? So the granule porosity we can calculate from the internal voids and the overall volume of the solid. Okay, that will include both solid and the internal void, volume space. Okay, so again, you can calculate the apparent density. I believe I thought I had the derivation for this, but that's okay. It's a simple derivation, right? So if you know one of those values or two of those values, you can calculate the pore space, right? If you know the true density and if you know the apparent density, you can calculate the pore space or internal pore volume. But the challenge will be again getting the true density value, right? Any questions? Again, getting porosity or pore spaces from the density values. Okay, we'll do one calculation too. Okay, so liquid pycnometry is very common, right? So, but unfortunately, it doesn't include the internal void space, right? So it's kind of gets the mass of the powder, all external voids, leaving out all external voids except the internal voids. Okay, so you all would have done this liquid pycnometry method, right? Many of you, at least most of you. No? You all would have had a class physical properties, at least ag engineers, right? Maybe you would have done a lab. You put some sample inside, and then from the change in volume, you get the volume of the solid. Go ahead. Yeah.
With the help of toluene.
Yeah, toluene is common. Okay, or any alcohol which has which is non-absorbing is very common.
Generally used.
Yeah, toluene it's not safe, so we at least there we don't try to use it. So we try to use some any alcohol will be fine. So.
Other chemical, which type of chemical used?
What's that?
Other chemical, which chemical used?
Rubbing alcohol, simple alcohol. Okay, that's again that's non-absorbing too. But again, the challenge will be alcohol. You'll have to make quick measurement. If not, they will evaporate. So then volume calculation might not be same. The other common method, many of you would have used gas pycnometry, right? Any of you used gas pycnometry too? No? So it's very similar like liquid, but we are using gas. Okay. So you pump gas inside these, powders, and gas, it's very similar to what we talked about sorption, chemisorption and physisorption, right? The gas fills into the void spaces, both external and the outer voids between our intergranular void spaces, okay, and then gets the actual volume of the particles. So you all know about you all know ideal gas law, right? Okay, so just use the ideal gas law. So the pressure and volume of one chamber, you equate the pressure and volume of one chamber to the pressure and volume of the other chamber. So you get the volume of the powder from that ideal gas law. Okay. So it's again very simple operation, again very easy to measure. Right. Envelope density, again we cannot, it's kind of shrink wrapping, right? So we cannot use liquid or gas here, right? So there is only one instrument actually that does that. It's micromeritics, they make this geopic that measures this envelope density. Okay. So what they do is they use a specialized small fine powder that's very free flowing powder, very fine powder, and those fine powders are pumped inside the solids, okay, and then the machine automatically calculates how much powder covers the individual particle, okay, makes an envelope around the around individual particle, okay. So from the volume of the particle, it's called dry flow, it's free flowing very fine powder. So from the amount of powder that is pumped inside, you get the volume of the solid, okay, and then the mass, and then you get the envelope density. Okay. This also is simple and easy measurement. Only thing you'll have to use this free flowing fine powders. Again, we talked about particle density, right? But we, though we are trying to characterize particle density, but we are using bulk powders, right? We are not using one particle, right? For example, if you're using gas pycnometry, you will take like 50 gram, 100 gram of powder and then measure the density, okay? Since, for small particle, getting the particle level simple density is challenging, we use this bulk powder method and try to get the individual particle densities from there, okay? So again, it's kind of correlating, the bulk density or bulk properties of powder to the individual level, particle level, property. Okay. Again, most common, envelope density or apparent density, again, it gives an average of density of the particles. Okay. So again, since we are using large amount of powders, we are not characterizing for single particle, but for a large volume, and then trying to get the single particle level values. Okay, so can we do a calculation? Okay, I forgot to bring the answer. You calculated some values yesterday, right? I have to check. I forgot to check. I will bring it tomorrow. Okay, so can you do this calculation? So it's a 1 mm diameter spherical particle with true density of 1 gram per centimeter cube. Internal pore volume is 0.1 millimeter cube, and then there is an external pore of 0.2 mm. So what will be the apparent and envelope densities? The simple calculation, right? So you know the true density, okay, you know the volume. So all the volumes are given. Maybe I can give this as homework, or can you do it quick? You all are calculating, or? You know the formula, right? You can calculate, right? So any of you had obtained a value for these? Did you guys calculate or did you get? No? Calculating? Trying? Yeah, that's why you putting those so that you all can try. 0.83? 0.96? Okay. Apparent density, okay. Okay. Should be close. I have the value somewhere.
I got apparent 0.7 and envelope 0.42.
Let me check. I should have the answer for this one. So. Apparent 0.69 and then envelope it's 0.427.
0.4269, sir.
Yeah,
Envelope one is okay.
yeah.
And the apparent is 0.745.
Okay, what I got was 0.691. So make sure you are putting all the values correct. So again, oh, it's not visible here. Okay. Let me show that so you all can. So first thing, again, we'll have to, sorry, my handwriting is not very good. Okay, hopefully you can understand. Okay. So you get the volume, you get the radius, it's a spherical particle, right? So you get the volume and then, use that to calculate. Okay.
Sir, 690. It's okay.
You got that? Okay. I might be wrong too. You don't have to match my value, but okay. So is that clear? So it's it's a spherical particle. So we get the volume, okay, and then all other things are given. So you just have to calculate. Okay. Any questions?
Why can't we use liquid or gas instrument for calculating the external force? It will cover the external force also.
Yeah, internal and external. Yeah.
Why can't we use that for calculating the envelope density?
So envelope density again, it's for individual particle, right? So it will be very difficult to get the gas. There could be some multi-layer absorption, right? So it's
Talking about density, it's only about every particle or unit volume.
yeah, that's what as I mentioned. Here we are talking about particle density, but we are not measuring for single particle. Still, we are if the particles are smaller in size, we use bulk powder to quantify single particle density. Okay. So we'll talk about that. Most commonly, if the sizes are bigger, we can X-ray. Use X-ray or other methods to get the density. Okay. But for small powders, this is what we do. Okay. Any other questions? If not, okay. So X-ray microtomography, again, if the particle sizes are reasonably big and if higher than the resolution of the X-ray, then you can use X-ray microtomography to get the particle density. Okay. So again, as we briefly talked about in the last class, it's easy. It scans at the resolution that you wanted and reconstruct the solid, and you can by post processing you can get the density of the material. Okay. You'll know the mass, you can get the volume of the particle from the X-ray, and then you get the density. Okay. So it's very, very highly used when it comes to agglomeration, granulation, etc. Okay. So again, most of the properties are influenced by particle density. Again, common density that we measure are true and apparent. Okay. But envelope, it's not, only one instrument manufacturer, so it's not very. So gas pycnometry can be used, again for apparent density, but, very accurate measurements we can get from X-ray microtomography. Okay. Okay, so there are some standards that talks about particle density, some references, etc., etc. Okay. That's it. Yeah. Any questions?
Sir, for like after every lectures you showed some standards for like
Yeah.
everything. So do we need to memorize or remember that for
No, you don't have to. That's just for your reference. So just to show that, there are standards for almost all property measurements. So if you are measuring some property for your research, then you can always follow some standards that will be useful. Okay, so let's move on to the next one. So in this part, we will talk about powder density. Okay. So we just talked about particle density, right? Again, very similar, but powder, it's the bulk material, right? So why powder, bulk density is important? Again, I've given one example here. It's very important to know the densities when you're shipping and handling, right? It's an example of filling grains in a large, rail car. It's a truck. Okay. So if you know the bulk density, you can, you'll know how much material you are putting in large container or even small packs, containers, etc. So again, almost very similar to particle density, the bulk density also influences all the flow, disintegration, mechanical properties, shipping efficiency, product, performance, etc. We'll go through some examples. Okay. So when it comes to flowability, we'll talk about flowability in the next lecture too. Okay. I'm not sure how many of you heard about this term Hausner ratio. It's developed by Hausner. So from the ratio of tap density and aerated, or rho A is the aerated bulk density or the bulk density, as we simply say. Okay. So based on this relationship between the tap density and the bulk density, he tried to assess the flow behavior of powders. Okay. So again, this is a common, very commonly used by most of the powder industry. It's not a quantitative indicator of flow, but it gives a qualitative indicator of how well the powder might flow. Okay. So using those two values, and this Hausner ratio is also directed to CARS index. Anyone heard about CARS index? No? You're done? Okay, we'll talk about that too, in the next lecture. So CARS index talks about compressibility. So this Hausner ratio is also directly related to the compressibility of the material. Okay. So if the bulk density and the tap density are almost same, then the compressibility will be low, right? So it's not changing. When you tap, if there is no change in volume, then the bulk density will be very same as tap density, right? But if the material is changing in volume when you tap, if it's reducing in volume, then the tap density will go up, right? So then their compressibility value will also be high. Okay. So many times you might have seen, that's one advantage of filling with gases, right? So it doesn't change volume much. In packs, when they are packing food materials, either it's if it's vacuum packed or if it's packed with gas, then the volume remains constant. At least the consumer will not think that I'm getting reduced quantity of material for the same price, right? So it's very important when you are shipping, etc. Okay. So if you are filling powders in containers, the volume should remain the same, right? At least for consumer, if they take 2 bottles, the level should be the same, right? So if the tap density is high, if one bottle is going through vibration and shaking process, its volume reduces, right? So the consumer might think, okay, it's not, I'm not getting the value for money, right? So these are, again, important when you are, handling and shipping, okay? So again, Hassner, we'll talk about this in the flow lecture too, but based on this relationship between tap density and bulk density, he defined a subjective flowability, okay? So as I said, if the compressibility is low, or if the, bulk density and tap density are very close or very similar value, then, the Hassner ratio is, very low, that indicates the powders will have a better flow behavior. Okay. If it's not compressible, then it might flow very well, okay, when you are like, transporting and handling. But if the tap density is, high, if it's changing a lot, then the Hassner ratio value goes up, and that will indicate, poor flowability of materials, okay. But again, this is also used for characterizing fluidization of materials, okay. It also influences, not sure you would have, we saw a chart in the fluidization chart, right, in one of the lectures before. Anyone remember? It's a Geldart chart that, relates density and particle size and their, fluidization behavior. No one remember? Anyone remember the Geldart chart from previous lectures? Okay, so I mean, you might remember when you check back. It's a relationship between particle size and the density. Okay, so you might have seen like 2-3 lines inside. So in one part of the section within the graph, that will show good fluidization behavior of powders if their relationship is in that area. If it's very fine powder, it's very difficult to aerate. If it's large size particles, then also it will be very difficult to fluidize. I gave an example of popcorn, right, popping. So it will sprout, then fluidize, right. So same thing, Hassner ratio can, indicate the fluidization behavior of these powders too, okay. So again, how it affects the porosity or mechanical properties? Again, in general, the porosity or the change in values of, the property can be directly related to the porosity or void space, change in void space, okay. So this P can be anything, it's a property at 0 porosity, and P will be the actual porosity value, actual property value that you are measuring, okay. It could be bulk density, it could be air tap density, etc. Can be related using an exponential relationship, okay. So again, alpha is the fitting constant, again F1, F2 are constants that we can derive from those relationship between void space and the change in property value, okay. So again, one big challenge of using this relationship is extrapolation to 0 porosity. So if you, if you extrapolate these values to 0 porosity, you get wrong values. So you cannot extrapolate to 0 porosity, okay. Other than that, it gives a reasonable estimation of the change in properties, based on the change in void space, okay. So when we characterize density, we are characterizing the void space, right, the pore space. That's what we are doing, right. So where and when and how the void spaces are changing and how it's influencing, is that what we characterize in different types of densities, right. Again, as I just said, Spriggs equation, that's the, direct exponential relationship. So almost, fits well, the properties, and as I said, only, challenge will be extrapolation to 0 porosity, then the values might be wrong, okay. But other than that, it fits well with most of the properties, okay. Any questions?
Can you please move to the previous slide?
Okay. So you might be wondering why we are talking about Spriggs equation in bulk density, right? it's the same. You have the values, right? But if you draw the line to zero porosity, this value might not be the actual value. That, it's very difficult to measure at zero porosity. But this equation says we can go up to zero porosity. You see, P0 is a property at zero porosity. Is that clear?
So the fitting constants,
Yeah.
where will you get that?
The fitting constants? Yeah, from
If I wanted to.
the fits. You plot it and then fit it. Okay. So again, the intercept is the P0 value. Okay. Oh, Young's modulus, by compression usually. What's usually we measure by uniaxial compression. Uniaxial compression. Yeah. We'll talk about Young's modulus, all those things in the last part of the lecture. Okay, how we characterize Young's modulus.
And sir, when you are using this, we will get the Young's modulus. And how will you just correlate that to mean porosity? Like for a porosity, we'll get a Young's modulus. And how will you correlate this to?
I don't.
We are doing this like uniaxial compression.
Yeah.
Then we will get the Young's modulus.
Mm.
Then we'll get a stress corresponding to strain.
Yeah.
Then we'll correlate.
Yeah.
We'll get the mean porosity from this.
So that's what you are compacting at different forces. So you will compact at different forces, then you get compacts with different porosities. For example, if you're using compacting at 50 megapascals, okay, so your void fraction will be different than when you are compacting at 100 megapascals.
How will you get that? How will you know that for that pressure you will get that porosity?
Or it's by it's not that's by experiment, one thing. Okay, so you'll have to compact and then measure the porosity.
First we have to compact the powder, after that we measure
The porosity, yes, yeah. If not, so right, so from the true density and the apparent density, so you can get the pore space, right?
Yes.
So you can use that, we'll do an example too in this, you can get the porosity, bulk porosity of compacts, okay?
We have to check different pascals. We have to check value of the Young modulus.
Yeah, so Young's modulus, if you change compression, it's stress over strain, right?
Okay,
So, yeah. So you'll have to change stress and strain values and then you get different porosity. So this, don't go into the graph too much, I'm just showing as an example, okay? We'll talk about these properties in the last part of the lecture, okay? Young's modulus and other stuff. Okay, so we talk, you all gave good replies, right? We characterize lots of different densities, right? One common density that we calculate is the bulk density, right? So for any powder, bulk density includes all the void space, or volumes and all the intergranular void space, right? So if you have two powders, you take the void space and include that in the overall volume calculation, right? So if you include all the void space within the bulk, okay, so the density that we characterize from that is the bulk density, right? Mass of particle plus mass of voids plus excuse me, volume of solids and volume of the void space, okay, right? You all would have done, you all know bulk density, right? It's a simple measurement, okay? So from this bulk density we can get the void fraction, right? So amount of void space within that bulk powder, right? So void fraction again are the porosity we can calculate from the amount of voids and from the volume of solids, right? So if you just use the volume of volume of voids over the total volume, you get the porosity, right? Or the total pore space or the void fraction within that bulk powder. It's not clear?
Sometimes if your void fraction is given as volume of voids by volume of solids, the volume of voids when into is called porosity.
Yeah, so it's a total volume. You just say total volume, volume of voids over total volume.
That's called porosity.
Yeah.
And when it's fraction, it's volume of void by volume of solid.
Yeah.
We use that usually. You were saying that porosity and void fraction both are same.
Yeah. So it's, porosity, it's usually, 100, percentage, it's fraction. So it's in decimals. So void fraction, if you're saying void, it's fraction, right? So it's always in decimal. If you multiply by 100, you get porosity. Okay. It's the same thing. So. Okay, so again, using those mass of solids and volume of solids, you can relate, to the bulk density and the solid density of the material. Okay, so if you know the void spaces, if you know the, bulk density, you can calculate the solid density, or vice versa. If you know the solid density and volume of the, voids, then you can calculate the bulk density. Okay, so it's again, you all would have known, this relationship, right? Calculating porosity from bulk density and solid density, right? Very commonly we use, right? Yes or no? Ankur? Yes, okay. Okay, so again, almost the opposite of void fraction is a solid fraction. So solid fraction is the amount of solid material without counting the void space within the bulk, okay? Solid fraction, you can see this volume of solids over the total volume, okay? So again, that will be 1 minus, void fraction, right? So if you remove the void fraction from 1, you get the solid fraction. Okay? So again, volume of solids over total volume, almost same, relationship you can get if you know the solid density and the bulk density of the material. Okay? And it's also called as, if you see someplace, if terminology called relative density, that's the, solid fraction is called the relative density. Gives the ratio of bulk over true density. Okay, that's called the relative density. Any questions so far? Okay. So solid fraction, I'm not sure, you might have not studied about, packing. Do you study about random packing or packing unit? In probability, maybe? I don't know if you study, but so in general, the maximum solid fraction for spherical identical sized particles will be about 0.74. That's the maximum, packing you can, get. But this is a large topic, okay, packing of particles, but I've given one example of how they pack fruits, right? So if it's spherical identical size, the maximum solid fraction you get for spherical particle is 0.74. Again, there are different, packing methods that call, packing methods, regular Hessian packing, cubic close packing. This is a picture for cubic close packing. Again, when one particle or one spherical particle is touching like 12 other particles, that's like very close packing. Okay, so if it's very close packing, then you get a maximum solid fraction of 0.74. Okay, and if it's random packing, it will be little less, and then but typical solid fraction for a spherical particle is 0.6. Okay, so that's what we try to change by compaction process. Okay, so change the solid fraction by compaction, so making it closer. Okay, again, a range of solid fraction, if it's a fine powder, in general it ranges from 0.2 to 0.5, but if it's compacted powder, usually it ranges from 0.8 to 0.9, okay, in that range. Okay, that means you are removing almost all white spaces within those powders. Okay, well, this example that I talked about yesterday, Tums is, talked about gelicyl, right? So in general, their porosity will be higher when compared with aspirin and acetaminophen. Okay, they are like nutrient, sorry, not nutrient. Medicine has to be released slowly, right? So their porosity will be low. Okay. But for Tums or gelicyl, which are immediate release kind of medicines, then their porosity will be a little higher, so that the fluids in your stomach can act quickly and then release the nutrients. Okay, so let's do this calculation. Okay, a powder, the true density of about this value is made into cubic compact. Okay, this is cubic 10 by 10 by 5 and has a mass of 0.5 grams. We calculate the bulk density and the void fraction of the compact. So again, make into a cubic compact, okay, and for the same powder, you are making into a cylindrical tablet. Okay, you are just changing the shape. Okay, and then how it changes the porosity. So if you change shape, it can change the porosity, right? It's a simple calculation. So by like kind of this simple calculation, you can see the effect of different particle properties on bulk behavior. If you change the shape, their values change. Same thing, if you change one property, other properties will also change. Anyone did the calculation? So which one will have a higher porosity, cubic compact or a cylindrical compact? Anyone did the calculation? No, not yet. Let me see how to get the values. Yeah, I should have it somewhere. You got the value? Anyone? No? So what's the porosity? 2? Anyone completed porosity calculation? No? How much? 0.2. 28, yeah, that's correct. So let's see, for 28.6 should be. Yeah. So which one has a low porosity, cubic or cylindrical compact? You don't have to do lots of calculations here, okay? So what's the volume of a cube here? What's that? What's the volume of the cube here? 500, right? So what's the volume of a cylinder here? So mass is same, right? So the volume is, for the cylinder, for the volume is low, right? It should be about 420 or something, volume of a cylindrical tablet, okay? So yeah, volume is low, right? So which one will have a lower porosity, cylinder or cube? Cylinder, right? So since, again, with the change in shape, you'll change the porosity too, okay? Point two, yeah. So since, that's what, you don't have to go until then there, just calculate the volume. From the volume, you'll know, the volume is low for cylinder than a cube. So the porosity will also be low, right? Okay, so common types of bulk density. So I believe you all, talked about this, right? So aerated bulk density, poured bulk density, tapped, compacted, etc. Okay. So can anyone guess what will be the difference between aerated and poured bulk density? I don't know why many are silent today.
Aerated means blowing air for some.
What's that?
Aerated means we are using air or any gas. Some.
Okay. Poured means you are just pouring. There will be still air, right? Yeah, it's very close, but but what's the purpose? Purpose of aeration or pouring. Okay, what's the difference? So aerated means, again, God, you have an answer? No, that's okay. So aerated means, again, you are aerating it so that you are removing the cohesive bonds between the particles. So they are individual when it fills in the volume or the container. Okay. So there are not any bonding between the particles that affects the bridging when it falls into the container. So for better accurate, again, characterization. So aerated bulk density, again, we don't pass air through it. Okay, so specific setup is, put in a funnel and make it flow through different, slabs, different baffles before it flows into the container which we use for measuring the bulk density. Okay, so when it flows through these baffles, those individual agglomerates or cohesive bonds are broken, and then the particles will be separate when it falls into this container. Okay, so there will not be any bonding between the particles that affects the void or volume calculation. Okay, so again, it's common. How many of you measured bulk density in lab? Most of you, right? So you make it flow through a funnel, right?
Yes.
And then it falls into a container, and then you get the weight, right? So that's a common. So for grains, larger materials, you will not use this kind of baffle assembly, but it's most commonly used for small fine powders. Okay. Bulk density, you might know, depends on the height at which it flows down to, right? If it's too high, then there will be chances of fluidization and you might be losing some powder. But if it's too low height, then again still there will be some agglomerates that will contain some bonding between the particles that affect the volume calculation. Tapped bulk density, again, you all know tapped bulk density, right? So you tap it for some amount of time, and then again you calculate the change in volume after tapping. Okay. So one of the major challenge will be again how many number of taps you can do. You don't know, right? So sometimes with the number of taps, the volume keeps on changing. But there are many standards to give an optimum number of taps you have to do. Okay. How many of you measured tap density? So for agriculture students, it's very similar. Like you put sample in a in a container, and then tap it like this. Keep on tapping. The volume keeps on changing. Okay. It's very very similar. If you're loading lots of material in a truck or container, when it reaches its destination, usually the volume goes down, right? Due to tapping, small particles will fill into the large, void spaces, and the volume goes down, right? That's what we will be quantifying using tap density. Okay. So again, we'll not know how many amount of taps, but there are studies and there are equations that gives that helps us calculating the number of taps that needed. Or you can if you wanted to characterize, you yourself can do some experiments and get the trial and error and get the optimum number of taps. Okay. So common is one sample instrument, but for grains and large materials there are large cylinders that allows us to tap in a big volume of powder. You can load the samples in cylinders, and then you fix the number of taps you wanted to tap, and then get the change in volume and get the tap density. Okay. Any questions? These are simple measurements, right? So you both are smiling. No, you can still smile, that's okay. It's okay to smile. Okay. Okay, so we'll talk about compressibility. Okay. Compressibility and compacted bulk density. Okay. So before going into it, again, it's very related to the bulk tap density. Okay. This, this equation you might see in powder papers a lot, Kawakita and Lude paper. So they related the number of, taps and their change in properties, that's related to their flow behavior, their cohesion, etc. Okay. So this N here is the number of tapping, C is the compressibility or compactability of the sample. So that's calculated from the tap density and the bulk density of the samples. Okay. So if you know the tap density, bulk density, so you can get almost, I'll talk about this N, A and B, these constants. You can, little bit know about their flow properties and their compressibility. Okay. So again, constant A is related to compactability, how much the powder compacts when you tap, and then again it's very related to the Carr's index. 1 over B, this constant is related to powder's cohesion and its flow behavior. Okay. So again, smaller values in general for A and 1 over B, it shows a better flow behavior. Okay. So again, number of taps, it tends to infinity, means again, you can go on increasing the number of taps, to get the tap bulk density, right? But at one point it kind of stabilizes, becomes constant. Okay. So again, this is a simple relationship, right? So if you plot N over C over N, versus N, you get a very linear relationship here. Tapping number, the ratio of tapping number over compactability or compressibility. Okay. So from these lines you get the slope and intercept that gives the constants A and 1 over B. Okay. So again, simple relationship, simple constants that can get you the get you more understanding about the powder bulk behavior. Okay. Are you still here? Okay.
Sir,
Yeah, go ahead.
now y-axis, what is the vector
Oh, what is that?
on y-axis?
So y is number of taps over compressible or compactability, C.
Okay, and x-axis,
X is just number of taps, N.
number of taps and
N over C. Okay. So again, these are some examples from Kawakita and Ludde's paper. So you see, there's almost the values are not constant. Some papers will some samples will have high and 1 over B values again, as we saw in the last slide. So lower values indicates better flow properties, right? Talc, all know talc, right? Surely their values are, the particle sizes are small, so their flow behavior will also be poor. Okay. But again, if you compare sugar and granular sugar, the values are close, but you can see the difference in A and 1 over B values. So A value is much smaller than the granulated sugar. The A value is much smaller than regular sugar. So granulated sugar is larger size, right? So their flow behavior will be better than small sized sugar powder. Okay. Again, there are, if you go into literature search, you will get lots of lots of values for different powders. Okay. Again, porosity increases with decreasing particle size, right? Again, we'll come back to that. Come back to that Kawakita and Ludde, and also the Hausner ratio and other things, when we talk about flow behavior of the powders too. Okay. So how does porosity, increases with decreasing particle size? So mainly the particles are cohesive, if there are some cohesive, forces between the particles, then they try to form clumping or bridging between those particles. That leads to increased porosity. Okay. But if it's larger size particles, you might know, if it's large size particles, their porosity is always high, right? But again, if it's for size powder, smaller size, uniform shape, uniform size powder, if you reduce the particle size, in general, if it's cohesive, their porosity will also go up. Okay. Mainly due to cohesive bonding between the particles that forms arches when you are pouring into bulk. Okay. Similar, moisture content, if you increase the moisture content, it reduces the porosity, right? So when moisture, if you increase the moisture content, water content will fill in the void spaces and pore spaces, and then, reduces the overall pore space or void spaces, right? So again, I'm just showing some, picture of small particles here. If you are increasing the water content, water fills into the void space and reduces the porosity of the particle or powder. Very similar, if the surface roughness increases, the porosity increases, right? So if it's very rough, there will be more mechanical interlocking between the particles. Okay. So if there is high mechanical interlocking, then the porosity will also go up. Okay. As you can see from small, again, picture here. It's higher mechanical interlocking from larger friction between those particles and forms into smaller arches and stuff, at bulk level. And this graph shows here, if the coefficient of roughness increases, the void fraction also increase. Okay. Too much theory, or is it okay?
Roughness, can you explain it?
What's that?
Roughness.
Mm-hmm.
How it is correlate increase or porosity increase?
Okay, so if the roughness is high, you can, simple example will be, if you take some fiber material, they'll be rougher, right? But their porosity will also be high, right? Because if you, heap some straw, usually what will happen, they interlock, right?
Yes.
Interlock and form into heaps, and there will be lots of white spaces inside, right? So that's what, this picture indicates. If it's highly rough, then there will be higher friction between those particles, and then they form into arches. Okay. Any questions before we go into compacted bulk density? No questions? Okay, I'll go back to one, example here. So it says, with, it's correlated this Kawakita and Ludde same fastener ratio to, it says that, with number of tapping, the change in density will indicate flow behavior, right? Right? With increased number of tapping, with change in powder property, when it changes volume during tapping, it indicates a flow behavior, right? You understood, right? Right? Is it clear? So what could be one major disadvantage of using this method to understand the flow behavior?
Incompressible flow we can't use.
Where do you see very close? Where do you see incompressible flows? At least in solids, not in fluids, but in solids. Like bulk powder flow. It's not about density. Any thoughts? But it's, again, we will talk about that in a minute. Whoever gives an answer in next 1 minute will get a chocolate. Okay. You'll have to think more. It's not a straightforward answer, but we'll talk about that in the Hausner ratio lecture 2. Okay. Any thoughts? Go ahead. You have? Go ahead. Yeah. So it's, we are relating here number of tapping, same like Hausner ratio, change in tap density to flow, right? Flow behavior. So if the tap density is not changing, if the density remains same after tapping, it will indicate better flow, right? Right? That's what they say. If the density is changing a lot, that indicates powder compressibility, right? Higher compressibility, that shows the powders will have poor flow behavior, right? But what will be one major problem with using that approach? Can we use that for all powders? We just talked about irregular shaped particles, right? I will give the answer, okay, but we will talk about that later too. So what happens, for example, if it's a very highly cohesive powder, for example, high moisture fruit powder, okay, the moisture content is like 30-40%, okay. When you tap, what happens? It doesn't change in volume, right? It remains the same. But does that mean it's a good flow behavior? It's not, right? So that's one challenge, So we cannot use that approach blanketly for all, for all powders. Same for highly irregular shaped powders. That might flow very well, okay. Since they are highly irregular, they form some interlocking, and then when you tape, the volume will change a lot. That will indicate it is having poor flow behavior, but in actual they will have better flow behavior. Okay. So, why I'm saying this is when you are evaluating powder, okay, just don't depend on the data that you are getting by different approaches. Make sure to understand your powder or characterize them very well, so then you can get meaningful inferences on their behavior. Okay. Just as an example, I said, if it's very cohesive and you are using Hausner ratio to get the flow, then you might write, okay, it's flow, it flows very well, but actually it's not, right? So someone would come back and say, no, this powder doesn't flow well, check back your values and stuff. So make sure to read through your data, think through your data when you are writing your thesis or publishing papers, etc. Okay. Just some suggestions, but we'll talk more about specific example in the flow lecture too. So we'll talk about compacted bulk density again. Just giving an example of grain bin. Not sure, I know it's not very common here, right? Grain silos, but still it's coming up in, at least in Punjab and some parts of India, or see lots of huge grains. So you'll see when you are loading samples in large containers, it could be a grain silo, or it could be a truck, or it could be a container. What happens due to the weight of the sample above it, it kind of compresses, right? So compresses the sample, and the density is also changing, right? So the powder may not have, or the bulk material may not have the same density at the top and the bottom. So the bottom the density might be high, the top the density might be low. Okay, so that's that's what we characterize from using compacted bulk density, and also for making tablets, compacts, etc. We use this approach. Okay. So at least for grain bins or large silos, why do we have to worry about this change in density? Any thoughts? What's that? Yeah, aeration, one good, that's a good answer. Aeration will change. If the density is high, the aeration will be poor. Go ahead. Yeah. Stability, not directly, maybe, yeah. It's not, it's a good answer too, but usually not. Okay. So it's bulk density, right? We are talking about bulk density, right? So what do we use bulk density for mainly? What do we use bulk density value for mainly? What do we have to measure for any material? Why do we have to measure bulk density? God, keep on. My question might not be clear, but still, based on your responses, I can modify the question. So what is the basic purpose of bulk density, at least for when you're manufacturing food powders? Packaging, exactly. So how much material you can fill in a container, or in a packet, etc., right? So the most property that's important is bulk density, right? How much you can fill in container. So it's the same thing for large storage structures too. So based on the density, you are changing the amount of materials, right? I'll give one example. So when they store these large amount of materials, usually they take insurance for those bins or whatever materials, right? So that they don't lose money if something happens. For example, if the bin breaks or bin fails, they most common, it's big industries here also, I think, will do insure their saved material. So if it fails, for example, how does the insurance company know how much material was there, right? They do not know, right? So yes, they can roughly estimate based on the volume of the container, right? But from the volume of the container, you can estimate amount of material present in there by using bulk density. But in actual, with compacted bulk density, there might be more material than the actual volume of material, right? So that's again one common place, at least in food and grain, where we use to get the actual volume of material, due to this change in density that we use for calculating, for multiple purposes. Okay. Same thing for shipping too. Inventory. For inventory calculations, how much material you have in the bin. So you'll have to use the compacted bulk density. So at least in the US and Canada, they use a term called pack factor. How much material is packing for grains, okay, at least for grains. How much is packed at the bottom. There are different constants for different grains by which they use to calculate the amount of material within the bin. Okay, again, that's one.
Is there any effect of weather in bulk density?
Weather, yeah, definitely. If you have higher moisture, then definitely the density will change, right?
Which been higher, a proportion or lower portion?
Okay,
If
that's
talking about a bin
wherever the moisture is absorbed. Okay, that's that's a good question, but you'll have to take my grain drying and storage class that I teach in 2026 spring at Purdue. Okay, no, that depends on the conditions outside. That there are multiple factors goes into play depending on the season. Okay, it can absorb in the top or in the bottom too. Okay, but we can say another subject like aeration. Talked about you told aeration, right? It's highly related to aeration of grain bins. Okay. So again, compacted bulk density. So how do we calculate this? By uniaxial compression, one-dimensional compression. So you put samples in a container and then just compact in one direction. Okay, you control the forces on all the other three sides and get just apply force from the top. Okay. And these are for generally for powders typical 70 or 75 mm ring diameters are common to get the compacts or compact densities, and again it can vary too, but these are common sizes for powders. One of the challenge will be, again, there will be wall friction, right, when you're compacting. That might affect your calculation of density. So you'll have to make sure that there is no friction on the walls that affects the compaction of the powder. Okay. Commonly used, what do you call it? I forgot the name. Starts with G. It's a, not glass, lubricant. So we apply on. Huh? What is it? Glycerine, maybe? Yeah. Is that glycerine? Yeah, it starts with G. Maybe glycerine. It might be wrong. It might be right. Okay. So some lubricant or low friction liners. There are like wax pipers. We commonly use wax sheets. Put it on the side and then compact so the friction is low. Oh, it's from the back. No. Someone had a question? No. Oh, grease use. Grease, okay. Grease, they become very sticky. Glycerin, I think glycerin is common, it's not very sticky. Okay. Or, most commonly, you use powders, like, very common is magnesium stearate. It's a powder, so what they do is compact with magnesium stearate first. So it kind of softens the wall and smoothens the wall, and then remove the magnesium stearate compact, and then you put the actual powder and compact. Then it will be very friction. Again, make sure you are using length diameter ratio of less than 1, so you can get the bulk density at different compaction pressures. Right? So you can correlate with the pressure or the amount of material at different heights within a large silo structure. Right? You all would have learned about pressure, right? Compaction pressure, calculation of pressure at in bins and silos. You remember the equation name? What's that? Those are for stresses, right? For calculating pressure at different heights. Yeah, Jansen's equation, right? So that's very commonly used, right? No? I don't. What? Can you repeat it? Grain? Okay. Is it used for solids, powders? Huh? Grain structures? So what do they calculate? Lateral pressure? Okay.
So both lateral and vertical. And
Okay.
also the load you can calculate.
Okay. Okay. Yeah, we usually, I don't know, I commonly use Jansen's theory. Yeah, I don't. Okay. Yeah. Jansen's theory. Yeah. Powders also Jansen's theory is common, so I never use. Maybe I should check that out. Okay. So which textbook it has? Okay. Okay. Oh, okay. Saha and Singh book. Okay. 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 I will check that out. Okay. So again, there are different, compaction equations. that you can use for relating the powder properties, change in properties. You don't have to worry about this again. Based on change in stress, you get the density of the powders. Okay, so at different stress values, you get the density. Again, there are tons of equation, but most common ones, we'll talk about Haeckel relationship, Kawakita. I'm not sure you would have learned about Jennings, Jennings and Johansson. Jennings, they have different papers, but Jennings and Johansson theory is very common when it comes to bulk solids, storage and handling. Okay. Again, so some of the best fitting models for compaction of powders that that relate stress and the bulk density. Again, Johansson is very common. Again, Jennings at very large stress values. So if the silos are tall, then you can use this Jennings relationship. Okay. Again, those are again simple relationship based on the change in density over stress values. Okay. So what happens during compacted bulk density? Again, I'm showing for one granular one material, but in bulk also it happens. So when you increase the pressure, the volume is also changing, right? The overall volume is changing, right? So there will be, you might have learned about, right, elastic deformation, plastic deformation, etc., right? So initially it goes through the elastic deformation. So when it exceeds the yield point, then you will get the plastic deformation, right? So the particle starts breaking, and then there will be the broken particle will fill into the void spaces and then make those dense compacts. Okay. So during compaction, again you can calculate the specific volume. That's called Walker equation, very highly used by pharmaceutical industry for when they make tablets, etc. Okay, compacts, tablets. Okay. Again, it's again the logarithmic model gives a simple relationship of change in volume. Again, it depicts the change in plasticity and elasticity of the powder, or plastic deformation and elastic deformation of the powder, and how it relates to change in volume when you are compressing the powders. Okay. So again, there will be sudden change in volume when there is too much, a high level of plastic deformation. Okay. Then again, the volume will not change until it reaches the final maximum density. Okay. Again, Walker equation that relates the change in volume to the applied pressure. Okay. So if you know the applied pressure, if you know the volume at different pressures, so you can calculate the volume at zero pressure. Okay. So again, volume at interparticle pressure is zero. Again, it's very similar like the other relationship that we talked about, the equation that we talked about. So in extra zero might give you wrong values. Okay, because actual conditions you might not see an interparticle pressure of zero, right? So there will be always some pressure between the particles from cohesion and addition between the particles, right? Right. So that's why you might get some error in the values. So again, just for summary, if you know the amount of void space in the powders or amount of actual solids in the powder, you can get the void fraction, solid fraction, etc. Again, all those other properties like shape, size, surface thickness, etc. will also influence the density and the porosity of the material. Right. Any questions? I'm not going to read everything, but any questions?
In Walker equation, lambda is showing the slope. What is lambda?
So the lambda is the fitting constant, but that can do again the porosity. Okay. So lambda is the fitting constant from the equation, okay, or the slope, intercept and slope. That's very similar to what we talked about in Spriggs equation. So V0 will be the intercept at zero volume, and then you get a lambda from the slope. Okay. So lambda, I didn't include all those things. So lambda will be highly useful when you are compacting powders, especially making tablets. Okay. So what will be the change in compacted powder when you change strain rates, for example? Okay. So all those information, strain rates, properties, etc. We can get lots of information from this change in lambda value. Right. And if you go, it's mostly used in pharma industry, but not much in food, unless you're compacting food powders. Okay. Any other questions? No. No question. So we talked about compacted bulk density, right? So before that, what time tea comes, Prakash? 11:15. You just seeing the clock and saying, 11:15, just randomly, no? Okay, that's okay. Okay, 5 minutes, okay. We'll talk about talked about compacted bulk density, right? So you know where we apply, right? So why do we apply bulk density? Why we need to know, right? Where it's useful, right? And where we use tap density, right? Mostly for shipping, packing, etc., right? So why do we care about the void fraction or the solid fraction? Any examples of application? Why do we have to quantify void fraction? Not why, let me rephrase my question. So any application where you want to know the void fraction within bulk powders? Any example application? Don't talk about shipping and handling. Okay, we already done with that. Any other examples that you can think of, where you will want to know, you should know the void fraction of the bulk powders. What is that? Yeah, so dissolution rate, right? So one common is dissolution rate. So if you know if its void space is high, then the dissolution will be higher, right? Any other examples? So did I go very fast, or is that okay pace, or is it very slow? How many of you think I went very slow? And I'm not your teacher, so you can be free and frank with me, okay? so that I can change for the other lectures, right?
Sir, one question.
Yeah, sure.
For aerated bulk density, should we use this in air classification?
Hold on. Before that, I'll come back to that. So one common application of why we want to care about void fraction is agglomeration again. So when you're agglomerating any type of powder, again, same thing we talked about binder load, right? Yesterday, how much binder you want to add. So this void fraction will influence the load of binder that you wanted to add during agglomeration process, so that you get good granules. Okay. Okay. So yeah, we'll come back to your question. Aerated bulk density and
Aerated bulk density.
and
So can we use calculate this for the air classification?
usually not. Aerated bulk density is almost, the purpose here, aerated bulk density, is just to break the individual particle bond and make them individual when they flow into the cup during measuring bulk density, right? But you can apply, how much aerated bulk density, as said,
So the air classification separation is based on the density.
maybe, yeah, it should be,
Like individual particles means there are range of particles.
yeah.
So individual particles have different density.
Hmm.
So based on that, like separation happens. So can we use this?
Oh, okay. So for that, more than aerated bulk density, your particle density will be much better. So that will give, a cleaner separation. So get the, particle density. For example, fibers particle density will be much different than protein particle density. So bulk may not give a cleaner separation. So you might, I'm not sure if you remember that Geldart chart, they usually use that particle density to classify their fluidization behavior. Okay.
So what other density I can measure? What other density I can measure?
For air classification, so particle density will be the one that will give you more information for separation of particles. So very simple, you would have known, you would have seen those winnowing machine, right? Screen cleaners that are used to separate grains from chaff. Yeah. So it's the same principle, air classification, right? So we use density, particle density of grains and the chaff to separate them into two streams. Okay. So it's almost the same principle, right? But here the particle sizes are very small. So yeah.
We can't segregate each particle.
Yeah. So that will be difficult. Any other questions? Come on, ask some questions. So I'll take this off. We are almost done for break. Okay. But I'm not leaving until for 2 minutes, Prakash. Okay. You said 11:15. Okay. So any other questions? Any other general questions? Nothing to ask. So ready to pack and go and drink tea? some people. Prakash, was the tea good? So when is the lunch? 1:30?
1:30.
I'm asking now because if not, you'll see the clock and tell. Do we have to wait or we can start? Do we have to wait?
Yeah, you can start.
Okay. Okay, so let's talk about powder flow. Okay. So what do you wanted to learn about powder flow? So why do we care about flow?
For conveying.
Conveying, okay. What else? Come on, what else? Conveyance, then? I showed many examples, right? What other properties are influenced by flow? After drinking tea, you all became silent. Was the cake too sugary? So why do we have to know about flow? Okay, obviously conveyance. Okay, what else? What you can think of? Sama, right? Shaima, okay. Tell Shaima what you can think about powder flow. Compactness, yes. Before compaction, it will affect how it flows. Okay. Showed an example of powder flowing into a dye, right? So if it's not flowing uniformly, then your compact will not be not good, right? So conveyance, packing, shipping, etc., right? What is it? Oh, okay, sand clock, okay. Okay, so what other thing that's useful of? Okay. Bulk, structure design, right? So these are some examples, pictures here. If it doesn't flow well, what it can lead to, okay? So like couple of examples, you can see bin failures, right? Bin is failing or falling down or breaking, right? So why does, how does flow is related to, bin failure? Abrasion, yes, yeah. So more than abrasion, wall friction. So that will be one effect. What else?
But that is a self-emptying system. If that angle is not positive and that is not supportive for the flow, it may block.
Okay,
That
yeah.
is it.
So yeah, we'll talk about some examples. If it's poor flowing, then there might be some other effects, right? But especially for bin failure, how does flow affects bin breakage or bin failure? So we talked about some equation, right? You said some, still forgot the name, Jansen's theory, right? So what's that?
Reinberg theory.
Rain?
Reinvert.
Oh, Reinberg. Okay, Reinberg theory, right? So what is the fundamental principle that they use in those theories?
Basically use that the pressure is not uniform.
Okay.
During hydrostatic we use P equal to H over G, but in that case it is not uniform. It
Okay.
won't like
Okay. Okay. So usually don't talk about pressure, right? Stress, right? Okay. So we use stress for calculations, right? So can you now relate why bin fails if it's not flowing? Gave a clue of stress. So what happens to stress during flow? Okay, stress increases. Okay. So example here is if there is non-uniform flow, okay, if it's not flowing uniformly, then there will be not positive or not equal stresses on both sides, right? So the stress will be non-uniform, right? It will not be uniform across the silo walls, right? So if pressure or the stress is not uniform, it will break, right? It will fail, right? So powder flow or any granular material flow, if you do not know well, you cannot design a good storage structure or bin structure. It can be small or large. We should know the flow characteristics of granular material. Okay, it could be for soil, fertilizer, food powder, anything. Okay, so those two. Okay, so can anyone guess what are these marks are? What's called? No, not corrosion. Okay, it's man-made marks. Okay. How does man make marks on the sides? Hitting, yeah, hammer hitting. So why do you have to hit? So now we talk about hopper angle. Okay, so flow, if it's very common in industries, what they do is they take a hammer and hit on the sides of the hopper so that the material will flow. Okay, this is again, I believe it's for pneumatic assistance. There are different flow aids, mechanical, pneumatic, etc., that makes powder flow. Okay, so there are again lots of challenges with flow of powders. Okay, fluids are much easier to handle than powders. Okay, do what we produce and market around the world? Do you know the percentage of solid materials in that marketed products around the world? How much are transported in solid form or how much are transported in liquid form? Any guess on a number, percentage? 10%. 90? Who said 90? Someone said 90. You said 90? Okay. It's very close. It's about 60 to 70% are shipped and transported and handled in solids form. Okay. So liquid form is very minimal. There will be always lots of challenges when we powder and solid material handling. Okay. Some of the common issues will be cohesive arching. If the material is cohesive, what happens is it forms an arch and then doesn't flow. Okay, so again you'll have to poke it or hit with hammer, etc., to make it flow. Okay, and mechanical arching, if it's like highly fibrous, high aspect ratio material, then it forms mechanical interlocking and then they wouldn't flow. Okay, again if you go to YouTube, there are tons of sample videos of this cohesive arching, mechanical arching, etc. Okay. Rat holing is another common problem. Again, these all are related to powder flow and hopper design, how we design the hoppers. Okay. Rat holing is like only the center part flows and the side is stagnant. So again, that increases stress on the bin walls and can lead to bin failures. Okay. If you have lots of rat holing, then it affects the strength of the bin, or pressure on the stress on the bin walls. The other common flow problems, again, if the outlet diameter, bin outlet is too small, you might get insufficient flow or pulsating flow. Pulsating flows means it flows, then it stops, it flows, it stops, etc. Okay. And low air permeability, if its bin diameter is very small, if it's not appropriately designed, then again, low air permeability. So how does air helps with flow? Or why and how air helps with flow? For example, give an example, if you go to a wheat flour, bulk wheat flour milling facility, large, who manufacture tons of wheat flour. So when they unload wheat flour, it doesn't flow very well, it's small particles, right? So what they do is they put another additional pipe to supply air through the, upper bottom so that it flows smoothly and easily. So how does air help with flow?
So if air and trap between the particles will be more, so flow would be
Okay.
probability will be more.
So what air is doing in between the particles?
It is increasing porosity and all,
Okay.
which help in.
Okay, increasing porosity, yeah. So that was very close, yeah. What else it's doing? Exactly, so it decreases forces between the particles. It could be cohesive, adhesive. So it decreases the forces, increases the interparticle distance. Okay, so when you decrease forces and increase interparticle distance, it starts flowing. The opposite of insufficient flow is flooding. Again, if you are not designing it appropriately, if the bin outlet is too big, or if the powder is very free flowing material like glass spheres, glass beads, etc., then you might see flooding of powders. There's no forces between the particle and they don't stop. It's just free flowing and flooding can occur. Okay, so all these again related to flow and appropriate bin design. Okay, so if you know the flow behavior of powder, you can design good bins or good handling devices. Okay, segregation another problem, right? So when you are putting bins, they always segregate based on size, shape, density, etc., right? Segregation will be a problem. Then when it flows out, for example, you are having a bin above a formula mix, powder formula mix. Okay, so if you are if there is too much segregation, the mix that you are making will be also be segregated, right? The quality will not be uniform, right? So segregation is a big challenge. Okay, so types of flow, there are more types, but I'm just using 3 of them here. Okay, so the common types, right? Funnel flow, mass flow, expanded flow. At least except 4 or 5 of you, most of you would have studied this, right? Saha and Singh book definitely should have these things, right? So funnel flow, as the picture indicates, only the center part flows, right? The sides are stagnant, okay, most often. And mass flow bin, everything is moving, okay. So a combination of these, so you can see there will be 2 hoppers at the bottom, okay. One is a mass flow, this is a mass flow hopper outlet and this is a funnel flow outlet. So you get an expanded flow, you get, most of the material from the top is moving and some of the material in the center core is moving. Okay? So when you see any kind of large silos and bins, you might see these 3 different types of flows. Okay? So again, you can see in a funnel flow, the sides are stagnant, right? But the center is moving, right? But it's very common, if you go to any industry, these 2 are very common types of bins you will see. Okay, large bin structures. Okay, either it will be a funnel flow or it will be a mass flow bin. Okay, and if you would have read again Saha and Singh book or any books, so what will be one advantage of a funnel flow bin? Since we know it's not flowing properly, right? Sides are stagnant, but still most of the industries use funnel flow bin. So what could be one major advantage? Or maybe there are more advantages, but what could be some advantages of using a funnel flow bin?
Segregation between in the corners can be avoided.
Usually there will be high segregation. That's one disadvantage of funnel flow bin. Where sides are stagnant, right? So larger materials usually roll off to the side. So what you get is a segregated flow. Okay. But what other advantage, what advantage that you can think of?
Sir, in this diagram, yellow one is blue
Blue one is stagnant material. Yellow is moving. Yellow is like flowing. Okay. What advantage that you can think of? Maybe you'll have to go back and read Sahai. You said Sahai book, right? Sahai and Singh book again. Or you forgot.
So it would describe the stagnant portion, first in, first out.
Okay.
For the remaining portion. That could be a disadvantage.
Okay. So usually it's the opposite. So in a funnel flow bin, it's a first in, last out. Mass flow bin is first in, first out. Whatever you put first will come out first. In a funnel flow, it's first in. Usually those are stagnant on the side, and the first in, what the material that you put later will come out first.
But for this portion,
Yeah.
this
So it's
portion is stagnant, that is okay, that will come at last. But the middle portion, that will come with the flow.
yeah.
It is before we load the upper portion.
So and again, it's a generalized diagram, right? So you are putting in, right, most of the material will be still stagnant on the side. Only some portion,
If that stagnant portion is too high, then that is
Yeah. You had,
No external aeration is required.
what is that?
No external aeration is required.
Which direction?
No external aeration. Air is required to move the flow.
Okay. But it's almost opposite. In funnel flow bins, you'll need more, flow aids and devices because it doesn't flow uniformly. Okay. So can you guess anything from here? Not the color, but overall picture. Size of the bin. Okay. You can see if you check the hoppers, if you are constructing a mass flow bin, the size of the hopper is too big. Okay. For funnel flow bin, the size of the hopper is small, so you don't need the bins will be a little cheaper than a mass flow bin. Okay. So you don't need lots of space to construct funnel flow bins too, compared with a mass flow bin. Okay. So one other common advantage is, like if these bins are in a continuous flow stream. Okay. For example, again I'll go back to wheat milling industry. Okay. So wheat milling, you all know that wheat before milling they temper, right? Add some water and temper it so that milling is easy. You all remember or you all know, right? Right? Yes or no? No? Okay. So for some of you who you do not know, for before milling wheat is hard, right? External part is hard and starch is softer inside, right? So what they do is they add water. It could be by steaming, but mostly mixed with water. So the fiber will become little softer. Okay. So when it becomes softer, they break in large pieces than small pieces. If it's very dry, fiber will break in very small piece. Then separation will be difficult. Okay. So if you add water, they break in larger pieces. Okay. So from tempering, after tempering, it goes directly into the milling machine. Okay. So in that, above the milling machine, there will be a temporary holding bin. Okay, that's one example I'm giving, but most of the continuous processing units, you will see this kind of bin. So in that, type of situations, you will need lots of headspace here, right? Because you are tempering continuously, you are putting material inside continuously, you will need lots of headspace. So in mass flow bin, the headspace will be very small because everything is moving, right? So the movement will be slow. So you will have very limited space on the top, but in funnel flow bin you will have more space. So you can put more material on the top continuously. Okay, that's one, again, major advantage. But other disadvantages, the sides are stagnant, right? So there will be added pressure or stress on the walls, and then there will be high segregation. There will be rat holing issues. Again, flow may be uniform, etc. Okay. Mass flow is comparatively, it's taller. You'll need more material, little expensive, and need more space to construct than a funnel flow bin. Okay, and the flow is better, uniform, than a funnel flow bin. Okay. But can you think of one disadvantage from a mass flow bin other than the height and expense, etc. when it comes to powder flow property? One disadvantage that you can think of? That you can actually adjust. Discharge rate you can adjust. But the total overall volume movement discharge rate you can adjust. Any other disadvantage?
If powder is more cohesive, then it can choke the discharge.
Yeah, it can, definitely it can choke. There could be caking issues, but in general, caking issues are high in these funnel flow bins since they are stagnant here. Okay. That's a good point. Any other thing that you can think of from the picture at least? So everything is moving, right? So there will be always friction on the walls, okay? And then friction and stress on the walls will be a little higher than a funnel flow bin, right? So material is moving all the time, so higher friction on the wall. So again, the construction will be different for a mass flow bin than a funnel flow bin, okay? And there are again other disadvantages too. So just to overcome these difficulties, sometimes you might see an expanded flow bin with two different hoppers, okay? So you'll get both funnel flow and also mass flow pattern within the same bin, right? But when you go and see in industry, you'll see lots of tons of different designs of bins, okay? But usually overcome the flow issues by using some flow aids. There are mechanical flow aids, hopper vibration systems, flow inserts, etc., etc. There are tons of different things. Okay. Again, powder flow issues, non-uniform flow, tablet weight in a smaller level, again uneven flow segregation, etc. So this is a need for other powder flow aid devices like vibration systems, active feeding systems, etc. Hoppers, etc. Some examples, change in stress can lead to implosion also, and this is common, if it's not flowing. Most of the industry, 99% of the industry, that's what they do. Pick up a hammer and hit it on the wall so that it flows. Okay. This one example again, say grain silo. It's very common, grain silos failing. Okay. So almost, if you take one grain silos, you will have lots of millions and millions of bushels of grains. Okay. So usually tall and high, when it breaks, it usually floods. There will be lots of other challenges along with that. Okay, one is losing grain, the other is there will be other challenges too. Okay, so powder flow. You know about flow, right? So we'll talk about the definition too. What is flow? Just moving the material, right? Flowability, or how easy it is to flow. So can we define using this flow of particulate material using a single number? How any of you used or measured flow properties of powders? Huh? No, that's mostly for fluids, any other flow behavior, shear cells, rheometers. No one used. Okay, so usually it's difficult to define using a single number to talk about that. So we'll have to use multiple parameters, multiple properties to understand the flow behavior of powders. Okay, again, it behaves differently. Okay, so in general, solids, most of the solids will have some attitude issues. Okay, so because if it's air or liquid, it's just pure air or liquid, right? But solids will have both air, liquid, and solid, right? Three components, right? So their behavior will change based on the conditions. As you all know, if the humidity changes, if the temperature changes, their behavior will also change, right? So what can we measure? So what we can measure the powder that indicates their flow behavior or flow properties. I'm just giving an example here. At loose packing state, it might flow. If you consolidate it, it might not flow at all. But if you aerate, it will flow like a fluid, right? So depending on the conditions and depending on their properties, their flow behavior will also change. Okay? That's why when you're dealing with powders, you'll have to make sure that you're accurately quantifying their properties and their flow behavior. Okay. So again, variables, we'll talk about variables a little bit more. To consolidation again, consolidation influences a lot. I'll come back with an example in a minute. So if you consolidate, right, when you tap, it increases the particle contact and also reduces the porosity. So if porosity is reduced, there will be less permeability, then the flow behavior will be challenging. And same with aeration, moisture content, it increases both cohesion and adhesion when you have lots of water in there, right? So it will become sticky, right? It becomes sticky and then doesn't flow. Storage time, again, if you are storing powders for a longer time, it keeps on consolidating, right? From its own weight, it consolidates and then starts caking, right? Then it doesn't flow. And if you're putting those material that can cake in large silos, then the silos can fail or break. And again, temperature to irreversible property changes, caking, etc. Right? So any of you measured glass transition temperature? You all know about glass transition, right? So that again, for agriculture students, you might not know. Glass transition temperature is the temperature at which the property changes. Okay, so from a glassy state to rubbery state, okay, changes. Their molecular vibration level changes. That leads to property changes in powders. It leads to caking or other effects. Okay, again, that will also affect their flow and handling properties. So again, combining all, the major factors, if you have same uniform powders, will be the environmental conditions, right? The temperature, humidity, storage time, etc. That will have a large influence. Then again, shape, roughness, irregularity, etc. Right? So which we talked about size and flow, right? So larger size might have a better flow than a small size powders. Okay. Same with density. If the density is high, they might have a better flow compared with a low density material. Okay. Again, external factors, vibration, feeding, etc. Okay. I'll give you one example on effect of vibration. Okay. So you might have any of you seen any silo by a railway track, close to a railway track? Most often, it's not. They usually have some vibration control systems, because if you construct a silo near a railway track, there will be constant vibration from passing of trains, right? So it compacts the powder and then flow will be an issue. Okay, so just one example. But again, vibration is always a challenge. Okay, so we talked about liquids and rho GH equation, right? Pressure equation, right? So forgot the name, but she talked about rho GH, right? Just quickly, one question before we, I'll come back to that in a minute, in the later part of the lecture too. Okay. By grain silos or any other powder silos are shorter and taller. You all know, right? You would have seen those water tanks, oil tanks. They will be short and wide, right? But grain silos or any other powder storage silos will not be wide, but it will be shorter, but it will be very tall. Do you know why? Thoughts? Okay, think about it. I'll come back to that question during the later part of the class when we talk about stresses. Yeah, go ahead.
water, the whole load of water will come on the bottom.
Okay.
But the load of grains are compensated by the walls as well as the bottom.
Okay.
So grain silos can be taller, but water.
So in grain, it's not the exact answer, but very close. But in grain silos also you'll have load on the bottom, right? We just talked about compacted density, right? It's very close to load, but very close to the answer, but not the exact.
Sir, whole load of grain is not compensated by the bottom. It is compensated by walls and bottom.
Yeah, why and how?
Because of the friction.
Not about friction. I gave a clue, what she talked about, P equal to rho GH equation, right?
So in liquid, like that, like pressure will be uniform for all the sides. But in the grain silos, the thing is like if the grain silo size will be more, so load will be more. The area for the load will be more.
Okay.
So that we kept.
Okay. Second, when you'll understand when we talk about go ahead.
In case of liquid, buoyancy force difference in case of grains or powder.
Okay. Okay. So when you understand stress, then you will know about this. Okay. So again, we will come back to that. Okay. So again, simple equation for liquid, we use the simple equation of P rho GH, right? Density times gravity times height, right? So with increase in height, the pressure will also go up, right? Directly proportional to height, right? But for grains and material, the pressure doesn't go up directly proportional with the height. Okay, I'll give a clue. Just above 1 or 2 meter, there will not be any effect from the height. Okay, I think it's close to 2 meters above which, and again it depends on the powders too. Above that height, there will not be any effect from the height. But talked about, as I said, it's very close, right? It's there will be vertical stress and lateral stress from the grains, right? But the lateral stress will go up. Okay, so with the effect of large amount of grains. So to avoid the effect of lateral stress, okay, so see the vertical stress effect will be low, but there will be still higher effect of lateral stress. Okay, so that's why you make it smaller, but you increase the height, the stress effect will be very minimal. Okay, so again we'll talk about that in the later part of the class. So what are some of the traditional assessment of flowability? What is one common method that we use to get the flowability of material? We talked about that a lot. How do we measure flow? Like simple way.
Volume per unit time, that is.
What is that?
Volume per unit time, what is discharged through?
I didn't get it. God,
You asked about calculation, right?
no. How do we assess flow of material? You all do.
What you come in particular time.
No, that's discharge rate, but flow, okay, I have sugar and coffee powder. How do I know, how do I make a simple assessment which one will flow better? Gravity, moisture, maybe assume they are of same size and same moisture content. Measuring, I'm saying assessing and measuring. How will you, as I said, I have sugar and I have coffee. Okay. I wanted to just make a quick and dirty, assessment that, which one will flow better.
Which is happening to regular flavor, high mass, that will.
No, that's again discharge rate. So I'm not talking about discharge rate. I'm just talking about assessing their flow behavior. If I tell the answer, you will be all surprised, right? Go ahead. Huh? No, not airflow. Any one more quick guess?
Porosity.
Not porosity, but that will affect the other properties. But angle of repose. Okay. So that's what I said. If I tell the answer, you all will be surprised, right? So we just measure the angle of repose, right? So if it has, again, that's, I briefly mentioned that in one of the past lecture too, right? Angle of repose is a qualitative indicator of flow. It's not quantitative. You cannot use it for any design or anything, okay? So if it forms a larger angle, then their flow will be poor. If it's a smaller angle, then their flow will be better, right? But I briefly talked about Hausner ratio, compactability, etc., right? So we'll be using those parameters to get a qualitative indicator of flow behavior of powder too, okay? Flow again, how powder flows. So there is no single standard for measuring powder's flowability, okay? There are tons of methods, tons of materials, okay? But again, you'll have to choose the right method based on your end purpose, okay? And again, most times it's a powder's individual properties and their flow behavior. So property also plays a larger role when it comes to flow, right? So again, common, as I said, common qualitative indicator is angle of repose, right? So measure the angle of repose. It's simple measurement, right? So make it fall through a funnel, the height, the diameter of the cone or the pile, and then get the angle, right? As I said, if the powder is of poor flow, then it makes a larger angle or larger pile. But if it's good flowing, then it will be smaller pile and smaller angle, okay? But as I mentioned in one of the previous lectures, very challenging to measure for cohesive powders. For example, if you take this powder, you might see more than one, right? You can determine or calculate or see more than one angle on that pile. So which value is the angle of repose of your powder? It's very difficult to determine, right? So that's why it gives a qualitative indication, but not a quantitative measure that you can use for purposes. Angle of fall is commonly again used to get an indication. So it's you take a spatula, take a powder, and then give a small slight impact and see how much it reduced in height, okay? So that gives an indication of behavior. So if the falling height is very low, then it has a better flow property, okay? If it's still intact after the after the impact, then the flow property may not be good, okay? Same thing again, angle of spatulas. Insert a spatula into the powder bulk and see the angle of that powder in that spatula, okay? These are again simple qualitative measurements, okay? You can easily compare between powdered sugar and granulated sugar. All these will give good differences when you use these measurements, okay? So in general, again, these are commonly used drained angle of repose. So if you do not have a hopper, if you are storing materials in bulk bins, you drain the material, and the angle that makes on the side is called the drained angle of repose, okay? This can be used to calculate the amount of material that will remain in the bin after you unload all this stuff from the bin, okay? So another common angle that's calculated is dynamic angle of repose. So it's mostly for mixing purposes, etc. So during mixing, how the angle of repose is changing, okay, within the drum mixer or during agglomeration, etc. Okay. So again, this is very simple to like other angle of repose measurements. You just need a rotating drum and a camera to measure the angle, right? So when it's rotating, how the angle is changing, okay? Again, mostly for mixing and agglomeration purposes, okay? So powder blends may have different angles of repose, so it will difficult to characterize. In general, smaller angles indicate better flow than a larger angle of repose powders, right? Some examples here, lactose, when you compare sodium chloride and lactose, sodium chloride may have a better flow property than lactose, okay? So First class we will talk about in a minute too, but again, if the angles of repose in the range of 25 to 30, they will have excellent flow. That means, flows very smooth, but if angle is very high, above 60, then their flow behavior will be very difficult. Okay. So in general, grains will fall in this excellent and good, flow behavior based on the angle of repose. Their angles of repose will be around this range. Okay, so what he did was in 1960, when we had lots of flow measurement systems, he developed two indices called flowability and floodability. Okay, and there is an instrument too. It's still a Japanese manufacturer makes those instruments to get car indices of powders. Okay. So again, flow, it's a measure of powder's ability to flow freely, while floodability is the powder's tendency to fluidize in air. Okay. Again, both are related to flow, but again, floodability is how easily it can flood, or how easily it can fluidize. Okay. So again, these are not from physics based, but what he did was he chose close to 3,000 different powders, dry powders, and measured different properties. I will talk about those properties, and then he made some manual judgment or criteria to develop these indices of flowability and floodability. Okay. So again, based on all experimental analysis and experimental measurement. Okay. So for flowability, he used angle of repose, compressibility, angle of spatula, and either cohesion or coefficient of uniformity to get the flowability index. So he gave like 25% weightage for each of these. So it kind of measures to 100%, and then if all these values are close to 25 and close to 100, that shows the powder is having good excellent flow property or flow behavior. Okay. So 4 properties, equal weightage, and then based on that you characterize the powders. Angle of repose, how to characterize, right? So compressibility, again, he calculated from the difference in tap density and the aerated bulk density. So I showed this equation during density measurements, right? Like in Hausner ratio, and this very similar relationship. If the tap density is very high, that means if the volume is changing high, or the change in volume is very high, compressibility will be very high. Okay, so that will affect the powder flow behavior. Okay. So yeah, again, for calculating aerated bulk density, what he did was like sifted powder through a sieve, so that they are like independent and not like bonded and agglomerated, and then calculated the aerated bulk density or the bulk density of the material. Okay. Easy, right? Or any questions? Any questions? Stop once more after that. Okay. Again, with we briefly talked about that. So when we tap, the volume changes, right? So if it's like if there are like mechanical interlocking or cohesive interaction between those particles, then they and the tap density changes. Okay. So based on this condition, so he gave some criteria of, like, for example, if the compressibility is high, then their flow behavior is exceedingly poor. Okay. So what will be one disadvantage of using this approach? Let me see if you remember that. Okay, fibrous material. What is that? You complete the sentence. Not fibrous, it's not non-uniform materials. Not ununiform, but it's more the shape of shape of the particle, and also talked about cohesion. So you just talked about, you all forgot. So I mentioned, right, so if it's very high cohesive particle, then the compressibility wouldn't change, right? That might indicate it's good flowing material, right? But in actual, it's poor flowing material. Same thing for non-uniform materials. But it will be free flowing, but it's non-uniform in shape. When you tap, the volume will change a lot. That will indicate it is having poor flow properties, but in actual condition, it's free flowing material. But again, these are again traditional assessments. So how he measured cohesion was again, so he sieved the powders using 3 different sieves, and again the size of sieve opening depended on the density of the particles. Okay, based on the density range, he used 3 different sizes, and from the their change in again working bulk the density is working bulk density, so that he used both the aerated bulk density and tapped bulk density, okay, to calculate that working bulk density and define 3 different mesh size by which you can calculated the cohesion. So take 3 meshes, take some amount of powder, and shake it for some time. Okay, depending on the amount of materials that are collected in each sieve, we calculated the cohesion of those samples. Okay. Simple and easy measurement, right? So based on the amount, then get the cohesion. So again, as the name indicates, decreasing cohesion will have a better flow, right? So any questions on this? Simple and easy measurement, right? So just take 3 sieves based on the density, and then shake them and weigh the material. Okay. And if it's for large size materials like grains and stuff, instead of cohesion, he used a criteria called uniformity coefficient. Uniformity coefficient. That's based on D60 and D10. Okay, so 60 percentile particle and 10% of the material. Okay, that is passing through some specific sieve openings. Is it here? Phone? Oh, okay. So if it's larger material, then again you get the uniformity by sieve openings. Again, increased uniformity. He characterized it, gives increased flow. So basically, again, as close to material, plotted everything. Again, if the values are high, then it has an excellent flow. If the values are low, then again it has like very poor flow properties. Okay. So again, this current is highly used to get the qualitative flow behavior of powders. Okay. Any questions? No. Any question? No. Okay. So the next one that he characterized was floodability. Okay. Floodability, again, the flowability, that's the one that he characterized previously. Okay, he used that flowability and then 3 other properties: angle of fall, angle of difference, and dispersibility, to get the floodability of the material. Again, as said, floodability is related to fluidization of the material, how easy is to spread, right? So if the value is same like flowability, if the value is close to 100, then the material is very floodable. Okay. That means it, again, easy flowing, free flowing material. You know about flowability, right? So angle of difference is the difference between an angle of fall. Okay. So what is angle of fall? Go ahead. What's yeah, exactly. So angle of fall. So you take powder in spatula and then give some impact, and how much it reduced in angle. So that's the angle of fall. Okay. So that's the angle of fall and angle of repose that you used to get the angle of difference. So in general, you can see, right? So if the angle is falling high, then it will have a better flow, right? If it's very cohesive, the angle of fall will not change much, right? So again, the larger the angle of difference, then it's easy or floodable material, like free flowing material. Okay. So again, simple measurement, easy measurement. Okay. For the dispersibility, what he did was like used a tube and then have some specific dimensions. This is an ASTM standard too. Now I think if you check on ASTM standards, you will see how to get the powder's dispersibility or even dustability, how much dust will evolve from during the handling of powders, etc. Right. So make the powder flow through the pipe and check how much powder still is intact in the same within that same dimension of that pipe, or how much based on the powder that spread across the watch glass or beyond the perimeter of the pipe, and how much powder that stayed within the perimeter of the pipe. He used that to calculate the powder dispersibility. Okay. So if it's not dispersible, then most of the powder will be intact. Here, if it's very highly dustable and dispersible, most of the powder will be again outside of this perimeter, right? That will show that it's highly floodable material or highly free flowing material. Okay. So again, same thing, he used those four criteria to get the floodability of the material. If the values are high, highly floodable, and if the values are lower, then it's not floodable. It doesn't flood at all. That's very difficult to fluidize. Okay. Any questions? Go ahead. Yeah.
Sir, how the number is given to floodability and
The flowability. Yeah. Yeah. So that's again his random assessment. It's not that he had used some physics or anything. Okay. It's based on random. So you can see equal weightage, 25 points for all the properties. Then add them together. If they are close to 100, then it's floodable. Same thing for the properties that he measured for flowability. If it's close to 100, then it's flowable material. Okay. It's based on his judgment of those 3,000 powders. Okay. Go. Do you had another question? Okay. Any other questions?
So when angle of repose and angle of fall are same, means the difference is zero in equal range. So how this two can be same?
So that means it's very highly cohesive, right? So angle of repose, take a spatula of powder, for example, you can say, thinking about some example powder like high moisture powder. Okay. Still. Gel? Gel is not powder, like it's like semi-solid, right? So, anything that you can think of high moisture powder? What? Raisins? Keratin? Okay, maybe I never used,
Refined with powder we can take as
What's it?
refined with powder, high moisture.
Yeah, milk powder still you will have some angle fall. Okay, so high moisture powder, cohesive. Maybe you can see some cooked rice or something. Okay, if it's uncooked rice, it will flow easily, right? But when you cook, it becomes very cohesive, right? You take a spoon of rice, cooked rice, okay, so the angle of fall, it wouldn't change. The angle of repose will be the same as angle of fall. Okay, so those places, it's like kind of those conditions, it's kind of zero. Okay, like high cohesive, moisture materials. Any other questions before moving on to the next part? And there are, standards again, as I said, there's an ASTM standard to get these car indices, again that's the, measure that's commonly used. Oh yeah, this is the instrument, Hosokawa micron powder tester. You just load the powder and it calculates flowability and floodability, and it has all the, and see different setups, spatulas and stuff, that characterizes. And for dispersibility, there is a, side, attachment along with that instrument. Okay, and again, it's, you will see mostly in, powder industry. Sure, break. 5 minutes. 5 minutes. Okay. Okay, 5 minutes break. So there will be always dust from road construction, right? Okay. So you'll have to calculate how much time it takes to settle, that dust particle to settle when there is road construction. Okay. Right. Can you calculate? For example, if it's a 50 micron particle, okay, can you calculate how much time it takes to settle? Yes? So what do you?
And actually we can calculate terminal velocity.
Okay, yeah, exactly. So if you know the forces, right, you just equate the forces, right, and then calculate the velocity or time it takes. So why it matters? How, we apply lots of, one is, how we, use mask, okay. So if the dust particles are suspended in air for a long time, then you'll have to use a mask, right? But if it's settling, maybe particle sizes are small, if it's settling sooner, then you don't, might not need a mask, okay. So like tons of applications. Wherever you go, you'll see application of particle technology, okay. So I want more experts from the group, okay, to work on different particle technology, aspects, okay. Okay, so let's continue with the traditional assessment of flow, okay. So we talked about Car's indices, right, and we briefly talked about Hausner ratio, right. Hausner ratio, that's the, ratio between tap density and aerated bulk density, right. So as we talked about, if the density, sorry, if the tap density changes a lot, that means the compactability is high, then the flowability will be poor, right. So and again, I should have in the next slide, again, this is a general classification. I skip, as I explained before. For example, if the cohesion strength of the powder is greater, so you can use all these, indices, Carr indices, Hausner ratio, etc. Said, you will have to make sure that you know the powder property well from your assessment before using any indices to characterize them, okay. Just some examples, okay. If the cohesion strength is great, tapping strength, then the initial, packing arrangement may not change. That shows a wrong value, right? So the tapping, the volume will not change, right? That shows it's a powder is of good flow property, but in fact it's high in cohesion, right? So it might not flow very well. And again, we talked about if the cohesion is high, angular particles, etc., the value that you get might not be the same as, no, we are not going to play a movie, okay? Don't get the wrong idea, okay? Okay. Okay, so again, there are many examples that are published in, literature that, shows good flow behavior, but wrong Hausner ratio values are, the other, okay? So we talked about Kawakita and Lude constants, right? So that can also be used to, assess the flowability of powders. So we know, from the constants A and B, we can get their flow behavior, right? So if the values are small, then the flow will be better, right? So again, N is the number of tapping and C is the compactability or compressibility that we characterize or calculate from the tapped and aerated bulk density values, okay? Again, smaller values, but again, it depends on the powder. Again, you'll have to tread with caution when you're using these traditional assessment of flowabilities, okay? Avalanche testing is very common. Again, very similar to getting dynamic angle of repose, okay? It's almost the same setup, okay? If you wanted to test, you can build a small, equipment in your lab. Only thing should be of plexiglass or glass. You have a light source and a camera that continuously monitors the angle of the powder when it's rotating, okay? So again, very easy. Only careful consideration should be the wall. The wall should not have high friction so that it's holding the powder. Then you are not measuring the powder behavior, but more effect of wall rather than powder behavior or powder flow behavior itself, okay? Again, as I said, very simple and easy testing. So you continuously monitor the change in angle at specific place within the tester. Okay, so you get the angle at which are the motion of powders at specific angles. Okay, so again, most commonly used in mixing, formulation, etc. Where it's very important to know the powder flow in a dynamic environment. Okay. So when you use these avalanche testers, I'm not sure how many of you have seen different flow behavior of powders in rotating drums. There might be more slipping motion, slumping, rolling, cascading, cataracting, etc., etc. Okay, so slipping is the powder slips, just the rotate, drum. Powder and the solid, or the powder could be its behavior itself. It's cohesive, it's not moving, it's as a bulk, it's slipping. Okay. Slumping is common, again, depending on the angle, it goes up a little bit and then falls. And then rolling and cascading are very common. It's these rolling and cascading are highly useful. This type of motion is highly useful to get the dynamic angles of repose or for avalanche testers. Mostly cascading, when you're doing agglomeration, this cascading operation will be, is that what you wanted? Okay, when you're agglomerating with binders, the motion should be cascading. It should not be like rolling or centrifuging, etc. Okay. Centrifuging, again, mostly if the speed is very high, if the RPM of the cylinder is very high, then you will see cascading, all powders sticking to the wall. And you saw the graph, right? So here the measurement of output or the angle. So if it's shorter and more reproducible avalanche times, then the flow behavior will be a little better. And again, smaller cohesion, smaller scatter means it's flowing easily. There's less cohesion affecting the movement of powder within that rotating drum. Okay. So there are again many studies that tested the drum speeds and to flow characteristics based on how much time it takes to avalanche, what is their avalanche behavior during continuous rotation, etc. Okay. One example here, these others, they calculated the flowability index again by testing the powders at multiple drum speeds and other characteristics. Again, same for cohesion index too. Again, based on the time difference, time it takes to avalanche, and the standard deviation between the avalanche times. Okay, so you can calculate or get some knowledge about the powder properties. Okay. This is, again, it's not actual physics based. It's a traditional qualitative indicator of flow. Okay. So again, as I said, friction we have to careful of. So if you are using a rotating drum or avalanche tester, the friction should be high so that it's not sticking to the walls. For example, if you are using a plexiglass drum, then it might stick to the wall than flowing or moving. Okay. If the particle sizes are small, there will be high chance of electrostatic forces. In general, anything less than 500 micron, there will be some amount of electrostatic forces. Okay. So and again, when powders are moving, there will be high formation of electrostatic forces between the particles, right? So you'll have to minimize them, during the flow. Again, you don't want to agglomerate the powder, right? So you are just measuring the powder property. There should not be any agglomeration. So that's these type of motions come into play. What type of speed or what type of powder property you have to adjust the speed, rotation drum, and also the amount of powder inside, so that you are not agglomerating the powder, but you are measuring the powder property. Okay. And again, it's mostly not recommended for cohesive powders. This other simple instrument, flow dice. I think I briefly talked about this. I'm not sure if you have one here at IIT, but very simple instrument. Make the powder flow through different sizes of orifices. Okay, you can see those openings are different for different orifices. So you take the size at which the powder flows uniformly, as the index for that powder. Okay, simple and easy again measurement, and mostly for measurements. Again, talked about comparing sugar and coffee powder, right? So if you wanted to assess sugar and coffee powder, this might be a quick and easy test to get their flow behavior. Okay. Again, does not represent, again, this is also a qualitative indicator, again, depending on the orifice size, we talked about cohesive arching, mechanical arching, etc., right? Sometimes a free flowing powder might not flow easily through those orifices due to other issues. So when you are using these instruments, make sure you know the powder well before using those values to report, okay, or use for other calculations. Any questions? What's that? So slipping means, yeah, no, I'm talking the difference, okay. So the powder is slipping here, right? So what happens in slumping, it's little slipping. So powder is carried along with the drum a little bit and then it slips, okay.
How does it differ from rolling?
What is that?
Rolling, how does it differ from rolling?
So, okay, rolling, it's not rolling the whole bulk. So once, some amount of top layer will be rolling, okay. So it's not all the powder is rolling, okay. So some top amount will be rolling. So that's, again, as I said, rolling and cascading are more useful for measuring dynamic angle of repose. Okay. Any other questions? Okay, so we'll move on to some physics-based measurements. And again, powder rheometers are not very much physics-based, but still a lot of industries have started using powder rheometers for its easiness of using them. Any of you used a powder rheometer? No. So no one is used. How many of you are using powders in your research? No one? Yes. You are? So you are using protein powder, right? So no one else is going to use powders? No one? So, okay, how many of you are using granular material in your research? Okay, you are, I know. Anyone? No one else? And you as you said. So what is the material you are using for your research? What's your research on? What is, yeah, it's you. This is a good technique, we do this during undergrad, okay. If, we used to be a large class, like we are close to 90 people in the class, okay. So when professor asked question, we used to turn back, okay. Many of you would have done that, right? If you don't know the answer, you tell, oh, okay, he's asking you, okay, not me, okay.
But as far as powders are concerned, like during my MTech, I have used starch.
Okay.
So that's in powder form only. But for rheology part, we
No, I'm just asking what is the material you're using for your PhD research?
So not yet.
Oh, you're not yet decided. Okay. Okay. You are using granular material, No one else? No? What is the material you are using?
Yes, I'm not really.
What did you use for your PhD?
I didn't use any.
Any? What did you use?
I work in spices machine design.
Okay, still you are using powder, right?
After that I'm using it.
Still, so how will you make the spice powder flow through the machine? You should know all these properties, right? I'm just, it's all, one way or other. You could develop machines, except if you're dealing with fluids, then you will be dealing with Same Ankur, you are using tomatoes, right? That's a large granular material, right? You should know the properties, right? So one or way or other, all those properties will influence, okay? So let's talk about some powder rheometers, okay? Perhaps we have 10 more minutes, okay? Right. So again, these are different types of powder rheometers, okay? Very common are like FT4 powder rheometer, as the picture shows here. It's very common, most of the industries will have, if you go to any food industries large, like Nestle, Mondelez, etc., I'm pretty sure they will have a Freeman, rheometer. This one from Andon Par, again another manufacturer. Andon Par, some of you would have heard, they are big in rheology measurements, mostly liquid rheology, but recently they brought out powder rheology too. Stable microsystems, if you use those stable microsystems, what is that? Compression analyzer, what is that instrument called? Instron, right? Texture analyzer. Any of you use texture analyzer? Okay. So that's manufactured by Stable Microsystems. So I don't have a picture. They also make a powder rheometer, but it's not highly capable of making lots of measurements like, an FT4 and Andon Par. FT4 and Andon Par are, again, highly used because they give lots of properties, okay? And then Andon Par, one more advantage is you can adjust the temperature and humidity too during the measurement. They have a different cell for, high temperature, high humidity measurements, okay? But in my experience of using these, we do have most of these in our lab. So Andon Par is mostly useful for low stress conditions, at very low stress, small stress conditions, then this gives a very good value. But FT4 gives good information when you wanted to handle materials, like how it flows in a conveyor, etc. Then it gives like good correlation, okay? But these are, are not connected to any physics, underlying physics of the powders, okay? It gives, as I indicated, it gives some relative ranking between powders, okay? One will have better flow, the other might have a poor flow characteristic. Very similar to Carson indices and, Carson indices and the Hausner ratio, etc., okay? But you will still get some value. You don't have to make some judgment call like in a Carson indices, okay? So what will be the property that will be measuring? Can you guess from the equipment setup? So it's flow, but what is actually measuring inside? Any guess? What's that? Viscosity, very close, yeah.
Cohesion.
Huh? Cohesion, yeah, that's a derived property, right? But what is a fundamental property that we are measuring, like force? What's that? Okay, I'll give you the answer. You might, if you're not used it, you might not know torque, okay? How much torque it takes for the spindle, there will be a spindle inside, for the spindle to move inside those powders, okay? So based on the torque values or differences in torque, you get the, other derived parameters such as cohesion, flowability, etc., all those values, okay? So I'll briefly, I'll not be talking about Andon Par, but I will talk about FT4. It's very common nowadays, It gives lots of, parameters like basic flow energy. I will talk about some of these, flow rate index, aeration ratio, permeability, etc., etc. So the instrument like this, it'll have a curved blade that passes through the powder, okay? So depending on the stress that you apply, the torque will change. So based on the torque, you get all of the derived parameters, okay? So again, basic flowability energy is very common parameter that's characterized from this FT4 instrument, okay? So that's the energy required to displace or move some amount of powders, okay? So how much energy it takes to convey or handle those powders, okay? And as I said, based on the torque it takes to rotate the spindle through the powder, okay, it gives all those all the parameters. Okay. So again, it's measuring torque, right? I was seeing whether I mentioned anywhere in that. So what will be the major property that will influence, at least in this measurement, basic flow energy? What will be one property of the powder that will have a larger influence? We talked about many different properties, right? Roughness, it's too in depth. Okay. Roughness will, all these properties will have influence, okay, but there will be major property influence. Can you guess? Compress, very close. Okay.
What is it?
No, yeah, okay, again close, but it's a density. Okay, I'll give the answer. Okay, it's all closer, right? Density and compressibility. Okay, so it's about density. Okay, so that density is the major parameter that affects this basic flow energy. So depending on the density, these values will also change. Okay, general nowadays I think system you can normalize using the density of the powder so that you remove the factor of density. Again, this is just an example from I think from my past work. You talked about spices, right? So if you have parsley, oregano leaves, and garlic salt, these all are spices, right? So if if you are conveying those, the energy will be completely different. Okay, again, it's high in density, right? So their energy will be completely different than oregano leaves and parsley. Those are like fibrous and lighter materials, right? So again, depending on the density, these values will change. Same thing with moisture content. Again, with increased moisture content, there will be increased cohesion, and that will also affect the density, right? So the total energy will also increase with increase in moisture content. Right?
Sir, only depend on bulk density or depend on other parameters?
So it will depend on other parameters too, but the major property influence will be from bulk density. Major property that influences. Again, surface roughness, porosity, all those will affect, but the major property interest here that influences this will be the density. Okay. So again, very similar to basic flow energy, it's a specific energy. So this gives a relation of how it flows in under low stress conditions. Okay. So if the powder is unconfined and if it's at very low stress conditions, then specific energy gives a good correlation. For example, if the value is 10 high cohesive powders, and if its values are low, then it's low in cohesion. Okay. So can you give one example of unconfined flow from an unconfined or low stress conditions from my previous part of the lecture, or from my first initial part of the lecture? Can you give one example of flow of powders? What is that? Where in hopper?
Like that, in that slant.
Okay, still very close. Any other thoughts? Yeah, it's actually answer is right. It's in hopper. Okay, but where in hopper? Not on the sides. Where you will see unconfined powder? Which part of the hopper you will see unconfined? It's not it's not confined. No. What's that? Top portion, but we are not making it flow from the top, right? So it's exactly from the reverse. It's from the bottom. So when you open the bin outlet, it's unconfined, right? It's free to flow, right? So that's unconfined condition. So if you open the bin bottom, then the powders are unconfined. They are supposed to flow from the bottom, right? So that kind of relates to at those conditions, flowing from unconfined or low stress environments are like, for example, if you're feeding in a spice grinder, okay? So when the material flows in, it's low stress, right? There is no stress on powders, right? That can also, specific also correlate with those conditions when the materials are flowing into a grinder or into a compacting machine, any kind of flowing into flowing in smaller streams. Okay. So permeability, again, how much passes through the solids, right? So again, one advantage of this machine is, change the stress or pressure, so you can check the permeability of or the pressure drop at different pressures, different stress or different loads. Okay, so that you can simulate to like large scale bins. So at different locations within the bin, you will see different stresses and different pressures, different loads, right? So you can get that by changing the normal stress and finding the pressure drops. Okay? So how much air will flow through those, solids. And, give me example from space. In general, the pressure drop for parsley will be high, for others, like oregano, pressure drop for garlic salt will be high. But again, parsley and oregano leaves will be a little lower. Okay. Any questions? Too much information, or yes? You don't want this? You want, okay. Okay. So very similar aeration. I know, if you are not using, but hopefully, down the road you might be using one of these instruments, either during your PhD or maybe even if you go and work for industry, you might be using one or other, powder rheometers. Okay. So again, aeration, how air passes equally through the powder bed. Okay. So this will help in kind of breaking those cohesive bonds, gets more idea about breaking cohesive bonds between the powders and making them flow. Very simple, a setup like the air measurement, but for example, the spindle will be still moving through the powder bed and measuring the flow of air through the, powder bed. Okay. So if it's very cohesive and, during dynamic, flowing environment, then the flow will not be, or the aeration will not be uniform. Okay. So highly, you can, to, simple kind of, you might, later on you might be using some, fluidized bed coating process, etc., right? You all know about fluidized bed process, right? So fluidized bed coating and all, that dynamic process, right? So you can relate these, this measurement to those processes. Okay, aeration. Okay, again, fluidization behavior, cohesion. So the flow energy for cohesive particles again will be very high compared to non-cohesive. So non-cohesive, the air will flow uniformly across the powder bed. Okay, I will stop here and we'll talk about shear cell testing tomorrow. Okay. So shear cell testing is the actual physics-based or math-based measurement of powder flow behavior. Right? So do you guys study, advanced math during MTech or PhD here? So what are the math classes you will study? You don't study any math? No math classes? Okay. No math at all? Yeah, BTech it was there. Okay. Not for MTech and PhD? Do you take any statistics class? How many statistics you take? 5 set?
No. I mean, 2 subjects. One fundamental, one advanced.
Oh, okay. Yes, I had those. These are fundamental calculations, shear cell testing. It's directly from the stress tensors and how stress flows, in bulk powder. I'm not sure, you can Google and see. Janicke did all these calculations in 1960s. So he developed those math and physics behind those powder flow. That led to those shear cell instruments, manufacture of shear cell instruments, etc. Okay. But I will not be going through stress tensors and stuff, it will be too much. As you said, it will be too much, right? No, okay. Any other questions? Prakash, I took 5 minutes extra. Yeah, you can stop. Done. Okay, so there's a lab at 2:30. Okay, so I'll see you all at 2:30.